The recent discovery of 15 new giant radio galaxies within the Sculptor field by the ASKAP telescope in Australia marks a significant leap in our understanding of large-scale cosmic structures. These radio galaxies are not only massive, spanning millions of light-years, but they also offer profound insights into the nature of galaxy formation, supermassive black hole activity, and the behavior of matter and energy at immense scales. Giant radio galaxies are extraordinary in their sheer size. While our own Milky Way galaxy measures about 105,700 light-years across, these newly identified structures are many times larger, ranging from 3.7 million to a staggering 12.4 million light-years in width. The largest among them, ASKAP J0107 2347, would encompass the Milky Way over 117 times, underlining its colossal scale. This level of enormity suggests processes of extreme energy and longevity, and investigating such phenomena could unravel long-standing questions in extragalactic astronomy. One of the most intriguing aspects of ASKAP J0107 2347 is its double-lobed radio structure. This feature comprises an inner set of bright, compact lobes and an outer, more diffuse and extended set. This dual-layered design is reminiscent of a cosmic nesting doll and could be key in explaining how these galaxies achieve such monumental proportions. The presence of two lobe sets indicates that the central engine of the galaxy, a supermassive black hole, may have gone through multiple phases of activity, ejecting energetic jets at different periods of time. At the heart of every large galaxy, astronomers believe there exists a supermassive black hole. These cosmic engines, when actively feeding on surrounding matter, create what is known as an active galactic nucleus, AGN. AGNs are capable of launching jets of particles at near-light speeds into space. These jets extend far beyond the host galaxy, interacting with the intergalactic medium to produce radio-emitting lobes. In giant radio galaxies, these lobes can extend for millions of light-years, far surpassing the boundaries of typical galaxies. The dual-lobed structure observed in ASKAP J0107 2347 likely results from a reactivation of the central AGN. Inactive periods are not uncommon for AGNs. However, interactions such as galactic mergers or influxes of fresh gas can reignite black hole activity, producing a second set of jets. These newer jets form the inner lobes, while the older fading lobes remain as evidence of past energetic outbursts. This stop-and-go cycle of activity could be central to understanding how radio galaxies grow to such vast sizes. Studying these phenomena requires specialized observational tools. High sensitivity, angular resolution, and low-frequency capability are all essential. ASKAP, the Australian Square Kilometre Array Pathfinder, meets these requirements through its 36-dish radio interferometer setup. By capturing high-resolution wide-field radio images, ASKAP enables astronomers to detect the faint, diffuse structures that are often missed by less sensitive surveys. The Sculptor field, which forms the backdrop for this discovery, represents the deepest field ASKAP has surveyed to date. Centered on the starburst galaxy NGC 253, it lies about 8 million light-years from Earth. Within this field, researchers uncovered not just one, but 15 giant radio galaxies, revealing a surprisingly high density of such colossal objects. This wealth of data allows for comprehensive studies into their shapes, symmetry, and age distributions. The vast lobes of radio galaxies are not only shaped by their black holes, but also by their environments. Galaxy clusters, where multiple galaxies are bound together by gravity, feature complex gravitational dynamics often referred to as cluster weather. These environmental conditions can hinder or redirect the expansion of radio lobes. They can create unique formations such as wide-angle tails, jellyfish tails, or the unusual merged structures like those observed in the Corkscrew galaxy. This external influence means that the size and shape of radio galaxies are not purely determined by their internal engines, but also by the surrounding intergalactic medium. As such, understanding the interactions between jets and their environments becomes vital. The ASKAP data allows astronomers to identify where radio lobes might have been disrupted or redirected, offering clues about the conditions in these distant regions of space. Old radio lobes are typically difficult to observe because they are faint and diffuse. However, the deep sensitivity of ASKAP's Sculptor field data has allowed for their detection. This ability to see both new and old structures in the same galaxy gives astronomers a kind of time-lapse view of galactic evolution. For instance, seeing inner lobes alongside fading outer lobes can help estimate the timelines over which AGN activity switches on and off, potentially spanning millions of years. ASKAP J0107 is especially valuable in this regard. Its nested lobe structure acts as a fossil record of multiple AGN phases. These kinds of observations are crucial for building models of AGN life cycles, particularly understanding what causes them to shut down and reignite. The ability to catch galaxies in these transitional states is rare, and ASKAP's depth and resolution make such detections more feasible. As ASKAP continues its sky surveys, it is expected to uncover even more of these rare galactic giants. The telescope's capacity to deliver massive amounts of high-quality data makes it possible to find and analyze uncommon objects like giant radio galaxies in unprecedented numbers. This opens the door to a statistical approach, where researchers can identify patterns across many examples, refining our understanding of galactic and black hole evolution on a large scale. The implications extend beyond just understanding how galaxies grow. By tracing the energy pathways of AGNs and their jets, astronomers can also infer properties about the intergalactic medium. The way jets propagate, fade, or get redirected tells us about the density, composition, and structure of the space between galaxies. This information helps fill in the broader picture of cosmic evolution. Moreover, this research aligns with the goals of the upcoming Square Kilometre Array, SKA, the next-generation radio telescope that will be even more powerful than ASKAP. Data from ASKAP serves as a foundational step, providing critical insights and experience that will inform future observations with SKA. The synergy between ASKAP and SKA represents a continuum of discovery, moving from the initial identification of phenomena to their deep, detailed understanding. The discovery of these 15 giant radio galaxies within a single deep field is not just a numerical achievement. It highlights how far observational astronomy has come. With tools like ASKAP, scientists are no longer limited to catching glimpses of cosmic giants. They can now observe them with clarity, trace their life cycles, and decode their interactions with the universe around them. As data continues to pour in from ASKAP, researchers expect the number of known giant radio galaxies to increase dramatically. This influx will not only confirm existing theories, but likely challenge them, as new and unexpected forms of galactic behavior come to light. ASKAP J0107, with its remarkable structure and enormous scale, is just the beginning of a new chapter in our exploration of the radio universe. The growing catalog of these structures will enhance our ability to model the physical processes behind jet formation, energy dissipation, and the effects of environment on galactic evolution. It will also refine our understanding of how black holes influence their host galaxies, sometimes over millions of light-years, far beyond their immediate surroundings. In the end, giant radio galaxies are more than just curiosities. They are markers of extreme cosmic processes and provide laboratories for studying physics under conditions that can't be replicated on Earth. Through telescopes like ASKAP, we can begin to piece together the complex histories of these cosmic giants and understand more about the universe's vast and dynamic architecture.